Hello Nilesh, you can hear me, right? Just wanted to clarify whether I'm audible or not.
Yes, you are audible.
Okay. Thank you. So we'll just wait for another 2-3 minutes and then we'll start. Okay.
Okay.
Okay, fine. So I guess we can start now. So welcome you all to this ninth problem solving session for this course titled Principles of Communication Systems. So today we are going to solve few assignment problems similar to what is given in week 9 assignment, and these questions can actually be solved within a very short amount of time using the formula that has been given, like discussed in the lecture. So what I would do is slightly different, like I would try to revisit the concept behind the question so that you will be able to answer the even if the numbers changes. I will mainly try to discuss the concepts that has been already been uh, given in the lecture so that it is helpful for you to answer similar kind of questions. So the first question we can see concerns with itself. It's a uniform quantizer which have a 128 quantization levels and maximum message amplitude is given as 1000. So what is the quantization noise power? So before moving into answering the question, let us briefly revisit the concept of quantization. So why quantization is even needed, as you have already probably know, but I will just briefly discuss it. So you have a message signal of this sort, and you then, for signal processing, you sample it at a different time instance. Let's say this is a TS, this is a 2TS, and this is a 3TS similarly. So if the message signal is termed as empty, so when you sample the signal at this time instant, so here you are basically getting some scalar value which corresponds to mts, m2ts, so on. Now one important thing to note that these scalars can theoretically take infinite number of values. So basically, if you plan to store them, these different samples, or to transmit them in both way, and if they can take infinite number of values, the issue is that you will quickly run out of the memory, which is the main concern in the signal processing. So what you plan to do, you basically plan to quantize these samples. So what I mean by quantize, so we are basically going to map these samples to a discrete set of symbols only. So you cut down the possibility of having infinite values. Let's say for example, these samples can easily take value like 1.31, 2.32, 4.39, and there are infinite such values possible. So it is not like it's impossible theoretically to actually store them, because you will need actually infinite number of bits to even represent one sample. That is the motivation behind quantization is as follows. You're basically going to map samples to a discrete set of values. So what I am mean by that, so hypothetically speaking, let's say I arbitrarily decide four possible values. Let's say uh, -1, sorry, -3, -1, 1, 3, and no matter what is going to be my sample value is, I am going to map them to one of these. So basically I have four quantization levels. So this is what about mapping samples to a discrete set of values. So I have easy time in storing and transmitting them. But the issue is, the moment I map samples to discrete set of values, error is going to arise. And how is that? Because see, uh, quantization is actually many to one mapping. Let me give a example that would be a bit clear. Let's say if the samples takes value between 2 and 3, I decide I am going to map all of them to 2.5, basically the midpoint of the interval. So what is the issue with that? It's a many to one mapping, you can see, because whether the sample value is 2, 2.05, 2.1, 2.93, all are going to be mapped to a discrete value of 2.5. So that is going to help you in storing and transmission. There is no issue with that. But the issue is, does this discrete value exactly represent the sample amplitude? You can see it doesn't, because any number between 2 and 3 is going to be mapped to 2.5. So it's not an exact representation of what your sample value is. It's an approximation kind of thing. So whenever you are doing this kind of approximation, there is going to be some error. So when I say many to one mapping, as you can see here, it is basically all sample in a interval is mapped to a quantization level, and whenever you do that, this leads to an approximation error. So what I mean by that, let's say you pick any number between this interval 2 and let's pick 2.75. So when I am representing 2.75 using 2.5, what is my error is going to be roughly it's 0.25, right? Now if the value is 2.5 itself, then you are mapping it 2.5, then there is approximately no error. So you can intuitively see where the maximum error is going to happen. It's basically going to happen at two extreme of the interval, because let's say the number is 3 and we are mapping it to a value of 2.5, so the error is the largest, 0.5. And similarly if it's 2, again you are mapping it to 2.5, so again the absolute value of the error, I'm not talking about plus or minus, the absolute value of the error is again going to be 0.5. So this approximation error we term as quantization error. Now this question concerns itself with the uniform quantizer. Uniform quantizer basically mean your quantization levels are spaced equally apart, right? So let's talk about a delta spaced uniform quantizer, where let's say the values between this interval minus delta over 2 to delta over 2 is mapped to a value of 0. Similarly delta over 2 to 3 delta over 2 are mapped to a value of delta, and so on. So this is what delta spaced uniform quantizer. You can see the quantization levels are all delta apart. So in this particular case you can see your quantization error lies in, okay, let me write it down, insert another slide. Okay. For delta spaced uniform quantization error lies in this interval delta over 2 to delta over 2 minus delta over 2 delta over 2. You can see, you can consider any of this interval. Let's say this any value in this interval is mapped to 0, so the maximum error is delta over 2 and the minimum is minus delta over 2. Similarly for this particular interval, if you subtract the quantization level from the extreme of this quantization interval, you can see in the both the cases the error is going to vary from minus delta over 2 to delta over 2. And in case of uniform quantizer, this quantization error is uniformly distributed. So what I mean by that, the probability density function you can basically represent with a rectangle of this kind. Since the quantization error takes a value from minus delta over 2 to delta over 2, this is your quantization error. and since the area under the PDF should be 1 and this length here you can see it's delta, so the amplitude of the PDF should be 1 over delta, so that area under this rectangle is 1. That is a fundamental property of any probability distribution function. Okay, by the way, this Q here is the quantization error. It is denoted by Q of m minus m, where Q is the quantizer which operates over the message sample, and this is the true sample value. So you can see that for actually uniform quantizer, it's the probability of is non-zero between this interval only, and outside it it's 0. And you can clearly see, since the expected value of
What is a QM?
QM is the Q actually denotes the quantizer function. Basically Q is operating over your sample, so QM is the quantized version of the this particular sample.
Okay.
uh, like did I okay, like am I able to make you understand, or okay, what I try to mean
I think
actually.
when you are solving the question, so just relate those numbers with QM.
Okay, okay. So for, let's say, if I talk about this particular interval, let's say your message value belongs to this interval, uh, minus delta over 2 to delta over 2, right? Then if I my quantizer operate over this message value, where the message takes value in the interval, then QM is going to be 0. So QM is basically the quantized value which can take only a discrete possible values, let's say 0, delta, true delta, and m is of course your sample value which can take like 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 any arbitrary value. So you can see the error, the PDF is symmetric around the 0, so it can take value from minus delta over 2 to delta over 2. So if I try to compute the expectation of this quantization error, so how do we compute that? Basically we'll have f q q dq and the interval over which it's non-zero, so that is minus delta over 2 to delta over 2. So this is 1 over delta, I can take it out, and this is q square by 2, and if I replace those values here, upper limit and lower limit, it would turn out to be 0. And it's quite obvious also because the PDF is itself symmetric around 0, so when you take the expectation of quantization noise, it's coming out to be 0. But more important quantity is expected value of q square, which basically denotes the uh, variance or power of the quantization error, and that can be computed similar to this only. Minus delta over 2 to delta over 2 q q square dq. So we have 1 over delta q cube over 3 running from minus delta over 2, delta over 2. This is 1 over 3 delta. Here we have delta cube over 8, and here we have minus delta cube over 8. So this will lead to uh, delta cube over 4. So this will cancel out, so delta square divided by 12. So the power of quantization noise is given as delta square over 12. Now comes the important step. When you talk about delta, it is a successive, it's the difference between successive quantization levels, right? So if I write delta is equal to the dynamic range by total number of quantization levels, that might not immediately make sense, so let me talk about the dynamic range here. So dynamic range basically means the maximum and minimum value of the message samples. So let's say the message can take value in this interval only minus mmax to mmax. So my dynamic range in this particular case is going to be 2 mmax. So the message can take value only in this particular interval, and that dictates the dynamic range. And when you talk about total number of quantization levels, it basically means how many discrete values are there. For example, if I have a dynamic range of, let's say, minus 10 to 10, sorry, the message takes value in this interval only, so my dynamic range is going to be, which I denote as dr, is going to be 20. Now if I decide to have only 4 quantization levels, so let me denote the number of quantization levels as L. If I have 4 quantization levels, what is my step size going to be? It's 20 over 4, that is 5. But for the same dynamic range, if I choose the number of quantization levels or the number of discrete values, you can see it in the both way as 16, then my step size drastically reduces to 1.25. So basically you can see that intuitively if we reduce the step size, that would leads to less quantization error. For example, in this particular case where step size is 5, basically the interval 0 to 5 is being mapped to a value of 2.5. So you can see the quantization error maximum value here. Sorry, quantization error takes values between minus 2.5 to 2.5, which is pretty huge value for L is equal to 4 case. But for the second case, L is equal to 16, it's only 0 to 1.25. 0 to 1.25, this particular interval is going to map to a value of 0.625. So you can say quantization error is pretty less here. It's from minus 0.625 to 625.
So quantization error will be less, but number of bits will be more. Am I right?
Yes. Whenever you are choosing the higher number of discrete values, your step size reduces. That is mean your quantization error is going to go down, but then you need more number of bits actually. So to have this L, if the quantization levels, so number of bits here is required is log base 2 L. So if I want to
Okay.
increase my quantization level, I need to have more bits per sample. So this step size, if I write it as 2m max, where m max is the absolute value of the maximum message amplitude divided by L. By the way, when I say number of bits, I denote it as B here. So if B is equal to log base 2L, then B is equal to log base 2L. So we can write L as 2 to the power B. And therefore my step size delta is going to be 2 m max over 2 to the power B. And I denote the power of this quantization noise or variance, whatever way we want to see it, as sigma q square. And this question here concern itself with the quantization noise power. So we are supposed to find the quantization noise power, and I would like to replace this value of step size in this expression. So you can see sigma q square is given as 2 m max divided by 2 to the power b whole square by 12. So we'll have 4 here, so that is 1 over 3. We have m square max divided over 2 to the power 2b. So this is the key equation for this particular question, where the noise power sigma q square is given as 1 over 3 maximum message amplitude square divided over 2 to the power 2b, where b is the number of bits required to represent each sample. So if I want to find the value in the dB scale here, which is also asked in the question, basically what we need to have, I need to take 10 log base 10 of noise power, and on this side if I do the same, I will have first of all it's 1 over,
Hello.
hello,
Hello.
hello, yeah, I can hear you.
Hello.
Hello.
Am I audible?
Yes, yes, you're audible. There was some issue on my side only. The Wi-Fi
Fine,
got
fine.
disconnected.
No issue. Okay.
So you
Will
can
you please share the screen?
okay, okay. Just a moment. Uh, you can see it now, or
Yes, it is visible. Thank you.
okay, okay, sure. Thanks. So this is 1 over 3. So if I want it to be 3, I will have minus 10 log base 10 3 here, and then I will have here it's m square, so there should be a 20, 2 times 10 log base 10 m max, and at the end I have here 2 to the power 2b, so minus 10 into 2b log base 10 2. So this value here takes approximately 0.3 something, so we'll consider it 0.3. So here we have minus 10 log base 10 3 plus 20 log base 10. The amplitude is given in the question as 1000. Okay, and next we have 0.3 times 10 times 2, that is 6, minus 6b. So now we just need to put the values here. So this here uh, log base 10,000 corresponds to 3, and we have 128 quantization levels. So b is basically log base 2l. So if I have l is equal to 128, that corresponds to 7 bits per sample. So we have minus 10 log 3 plus 60 here minus 42. So it's 18 minus, let me just calculate log base 10 3.
Scientific calculator is allowed in the examination?
About the examination that you are talking about, that physical examination, right, at the end of the course.
Yes, yes, yes.
Okay, I am not sure about that. I need to check the
Fine.
guidelines for that.
No, okay, okay, no issue. Thank you.
Okay. So log 3 takes a value of 4.77. So 0.477, so it's minus 4.77 plus 18 here, so that would lead to 13.23 dB. So we can see intuitively from here, for each bits increase here, the quantization power decreases by 6 dB. So for example, if I have, instead of using 7 bits per sample, if I use 10 bits, then my quantization noise will almost decrease by 18 dBs. Just some rough numbers to get idea about that. So yeah, 13.23. Is any of the answers matching? Okay, the fourth one.
Yes.
So let us move to our next question. So it asks about the bit rate of T1 system.
It is already discussed in the lecture. It is a 1.544 Mbps.
Yeah, yeah, true, true. So that's what, like, these questions can be answered pretty much straightforward, but since we have a lot of time, I plan to just reiterate the points that has been already discussed in lecture
Go ahead.
again.
No issue.
Yeah,
No issue. No
yeah.
issue.
So this T1 system.
Might be useful for the other students while they are listening this video after the recording.
Yeah,
So better to go ahead
yeah,
in
yeah.
detail.
I hope so. Like, it's helpful for others. So if I talk about T1 system,
Because this is my first online lecture for this course. I'm just listening your all the videos offline due to the
okay,
time is not matching.
okay,
So please
okay,
go ahead.
okay, okay, sure, sure. So this T1 system or telephony system is a like a very popular application in it actually works on the principle of time division multiplexing, which I plan to discuss next. So T1 system operates on the principle of time division multiplexing. So time division multiplexing idea is quite fascinating but also simple at the same time. So there are two parts. One is time division and second is multiplexing. So when you say multiplexing, it's about just putting multiple signals together in one or another way. And when you talk about time division, that basically means we are putting the signals together in the time domain. So what does that actually means? So you are taking multiple signals, let's say m1, m2, m3, these are all different signals. So you take the samples of them and you multiplex all of them together, like combine them to form a composite signal, and you then transfer this composite signal to some other, like for example in the when you talk about T1 system, it basically works on the principle of transmitting 24 voice channels over two separate wires. So let me write it down. So time division multiplexing here is combining multiple signals in time domain to form a composite signal, most importantly that can be transmitted over the same channel. So how do you do that? Basically you have this multiple signals here. Okay, let us first talk about the T1 system specifically. So T1 system multiplexes 24 different voice channels over two separate words and transmit them. So how does it work? Basically if I try to draw a schematic diagram kind of thing, so you have these signals m1 and then you have m2 up to let's say mn. So these are the signal you plan to multiplex in time domain. So first what you do as a cautious check, you pass them through low pass filter, and the purpose of doing that just to ensure the no high frequency component is present in the signal. So any undesired high frequency component is gone. You just want to ensure that. So we pass all of this through a low pass filter, And then what you do, you take samples. But here is the catch. How do you take the samples? You use a commutator thing. So this is what I call a commutator. It's basically a high speed electronic switching circuitry. So what it does, it connects to each of this signal over a particular time interval to collect all their samples. For example, first is you connect it to M1, you collect the samples, then onwards it move to M2, collect the samples of M2, and similarly up to Mn. And once you collect all these samples, so this is where you have this composite signal, where you have actually able to multiplex all those M1 up to Mn over the time domain, and then you are allowed to transmit the same over the channel. So commutator job is to basically multiplex different message samples. This is the job of the commutator. So I would like to get into slightly more details. Let's say this is what uh, M1 is. This is was M2, and let's say this is M3. So this is M1, this is M2, and this is M3. So now when like we are basically collecting samples, so when I talk about sample, obviously there is going to be a sampling period or sampling frequency. You can see it in either way. So the consecutive gap between two consecutive samples is what is my sampling period is. Let's say this is TS. Here I am assuming that M1, M3 they are all have the same sampling period. We are basically sampling them at the same frequency. So if I go back to this image here, what is the composite signal will look like if I plan to draw? So let me mark them with slightly different color. So M1 is red, M2 is blue, and M3 is purple. So my commutator will first pick this sample corresponds to M1, and then it will pick the sample corresponds to M2, that is denoted by blue. Next the purple one, and it will proceed so on. Now you carefully observe the different time difference between two samples of M1 is Ts, right? So every Ts instant the commutator should go back to M1 again. So let's say uh, this one is M1 TS, this one is M2 TS, this one is M3 TS, up to MN TS, and then from this place onwards again M1 will begin. So this entire duration should be TS or less than TS, because every TS instant M1 is going to produce a sample and commutator is supposed to collect it. So the sampling period of each signal is TS, and during this each TS period the composite signal is going to have how many samples? So this entire interval contains n samples. So the duration between samples in TDM signal, if I plan to denote it as T, is basically given by Ts over n. Given there this constituent signal M1, M2 up to Mn, they all have same sampling period. In that case, the distance between samples in TDM signal is Ts over n, because then only you can cover all n sample within this duration of Ts. And what about the, you multiplex the composite signal like this and transmit over the channel, fine, but then how do you recover it? So recover procedure is pretty straightforward. You can say basically the same, it's just the opposite way of this. You have this composite signal that is being received at the receiver end, composite signal. See, if you again have the commutator, and this demultiplexed output should pass to a low pass filter. So here you will have M1T, here you will have M2T, similarly MNT. Now the crucial thing is that if I call this commutator as CR and the receive commutator and the transmit commutator as CT, now for error free operation, for error free operation, CR and CT must be synchronized. So what exactly I mean by that, let's try the practical example. Let's say CR is delayed by Ts over n times compared to CT. So I am writing it here. So CR is delayed by exactly Ts over n compared to the transmit commutator. This CR is receive commutator, CT is transmit commutator. So basically there is a timing error of exact Ts of n. So can you say what will happen in that particular case if this they are not actually synchronized, but there is a timing delay between the receive and transmit error? Actually in that particular case you will see that you are starting from here basically. So this demultiplexed output will not be actually M1, it is going to collect the M2 sample. Similarly, which is here, which is supposed to collect the samples of M2, will now collect the samples of M3. So at the output of this low pass filter, which I was thinking I was obtaining M1T, M2T, essentially I'll be obtaining something, let's say M2 In place of M1 I'm getting M2, in place of M2 I'm getting M3. So for error free operation, this CR and CT must be synchronized. The timing synchronization is very crucial. If they are not time synchronized, then the entire situation will break down. So we next briefly talk about the bandwidth of the TDM signal or T1 signal, essentially the same only, because T1 function on the principles of time division multiplexing. We introduce a slide here. So you need to find the uh, just a minute. T1 system bandwidth. So for T1 system we know we have 24 voice channels, so 24 voice channels are multiplexed. And the sampling interval of each voice channel is TS. Now we know that voice signal basically ranges between this frequency range. So voice signal frequency range is roughly between 300 Hz to 3.1 kilohertz. So if I am to draw the frequency spectrum of the same, it would look something like this. This is 300, this is 3.1k. Similarly, this is minus 300 and 3.1k. So maximum frequency content here is 3.1 kilohertz. So my Nyquist frequency, in other terms, the minimum frequency I need to sample at in order to ensure the signal is not uh, distorted, is given as 2 times, this is FM, 2 times FM, that is 6.2 kilohertz. But essentially in practical systems we keep a buffer zone. So in practice, sampling frequency Fs is taken as 8 kilohertz. So basically you are kind of oversampling. Oversampling is not going to create any issue for you. It actually provides you a buffer zone, because if you uh, actually sample at Nyquist frequency, then you will have your spectral copies exactly close by, and there is no filter which have a kind of a sharp cutoff. So actually if you use practical filters and if you sample at Nyquist frequency, you are going to have some kind of distortion. So to avoid that, the sampling frequency is kept slightly higher compared to the Nyquist frequency, so as to ensure your practical filter, which doesn't have a ideal sharp cutoff behavior, can still be able to um, recover your signal without any distortion. So that's the only purpose. So we have already seen the spacing between consecutive samples of TDM signal T is given as Ts over N. So the bandwidth required for transmission of TDM signal FTDM is 1 over 2T, so that is 1 over 2 Ts over N, that is N will go above, N over 2 1 by Ts. So essentially we are going to have N over 2 Fs. So this is the bandwidth I require for the transmission of TDM signal. It's N over 2 Fs. N is the number of signals to be multiplexed. Fs is the sampling frequency of each constituent signal. So we have already seen the Nyquist frequency Fs for each constituent signal should be greater than twice the maximum frequency, and that means your transmission bandwidth required for TDM is greater than equal to n times Fm. So basically it says that bandwidth of TDM signal should be greater than or equal to number of signals involved times the bandwidth of each signal. So now we move to our question once to see in the T1 system. Basically once you have the samples, if we talk about particularly T1 system, mu law quantizer is implemented with 256 quantization levels. So if I talk about 256 quantization levels, you can immediately get the number of bits required to represent each sample, that is given by log base 2 256, which is 8 bits per sample. So the sampling frequency we have already seen Fs to be 8 kilohertz. That implies my sampling interval to be 1 over 8 kilohertz, that is 125 microsecond, and in this particular duration I have to fit the samples of 24 voice channels, and each of the in this 125 microsecond interval I have to accommodate 24 samples from each voice channel, where each sample is represented by 8 bits. So total, so this is, you can say 1 TDM frame duration. So total number of bits in the frame is given as you have 24 different samples from 24 voice channel. Each sample is represented using 8 bit, and on top of that you use one synchronization pulse. So you have total 193 bits. So basically you are transmitting 193 bits per 125 microsecond. So in T1 system we transmit 193 bits per 125 microsecond. So therefore my bit rate for T1 system is going to be 193 divided by 125 into 10 to the power minus 6. That means 193 divided by 125 into 10 to the power 6 bits. So this is just can be written as megabits, and this is what is 1.44. Sorry, 1.544 it is. One 1.544 megabits. Second one is the correct answer. With this, let us move to our next question. So it talks about a superheterodyne receiver with some intermediate frequency and the frequency of the local oscillator corresponding to an income signal of carrier frequency f1. So what should be the frequency of local oscillator? So there are a lot of terms here like superheterodyne, intermediate frequency, local oscillator, and carrier frequency. So I'm pretty much sure you have seen in the lectures also, but I will again reiterate few of the key concept here. So this question here, just a moment, this is relevant to a concept called frequency translation, or most popularly known as frequency mixing. Frequency mixing. And what is the motivation behind that? So you basically modulate a signal, and when doing the modulation you basically choose a high carrier frequency, right? So you transmit over your signal over a high carrier frequency, that's fine. And after receiving that, what you will do, if you are going to keep that same high carrier frequency, you are going to sample at a very high rate. So when you talk about the hardware requirements, so essentially if you move towards high carrier frequency, you will need a higher sampling rate. So higher sampling rate basically requires more expensive and sophisticated hardware. So essentially what is being done traditionally in the receiver end, so you transmit your signal over a high carrier frequency, fine, but once the signal reaches the receiver, the frequency is downgraded. That is, you translate the frequency of the modulated signal to a new center frequency. So the idea is something like that. You have a baseband signal that you want to transmit. This is a baseband signal centered around zero frequency. Now you do the modulation. So now your message is shifted to a carrier frequency of fc. This is fc plus fm. I'm not writing again. For example, if let's say your fm is like let's say 100 kilohertz, you are transmitting over, let's say, a carrier frequency of 2 megahertz or something. 2 megahertz you are transmitting over. But then what you do, you transmit, fine. no issues. But when this signal reaches at the receiver end, if we have still keep the high frequency, this center frequency you don't change, what will happen is that your you'll need to sample at a higher rate, which is not possible for inexpensive hardware. So that basically increases the cost and ask for more complicated circuitry. So what you do basically, you do the frequency translation. So this is FIF. So this is what called intermediate frequency, which is less than FC, and this procedure is known as frequency mixing. So the goal behind the frequency mixing is that shift the received signal to a new center frequency, which is also called as intermediate frequency. So after you do the frequency mixing, then you can do any kind of processing, like for example, after mixing the signal is amplified, filtered, and demodulated. But first you do the mixing basically to bring down the carrier frequency so that it's easy to operate over it. That's the only purpose. So the question is to how to achieve that. For example, you have this incoming received signal that you denote as xt is equal to mt cos 2 pi f1t. This is your incoming signal. This f1t is the carrier frequency, and mt is of course your message. So what you do, you basically multiply it with a local oscillator. Sorry, the output of a local oscillator. So the job of local oscillator is to produce a sinusoid at any frequency. So this is what local oscillator is. So let's say it produces a sinusoid at cos 2 pi f dash t. So basically you are producing a sinusoid using the local oscillator and you are multiplying it with the incoming signal, and then what you do, you pass it through a band pass filter. You pass it through a band pass filter, and what should be the frequency range of the center frequency of the band pass filter? It's f dash minus f1, and at the output you will get the message frequency, which is now modulated by the intermediate frequency instead of the carrier frequency, which is of course lower value than that. So we are supposed to find the frequency of the local oscillator. So for that we need to just calculate this and pass it to a band pass filter to obtain the result. So let us try that. Okay, so I am multiplying mt cos 2 pi f1t cos 2 pi f dash t. So what I'm going to obtain, 1 over 2 mt cos 2 pi f1 plus f dash t plus cos 2 pi f1 minus f dash t, or we can write the other way, f dash minus f1 t. So clearly you can see this Pardee sinusoid here centered around frequency f dash minus f1, whereas this one is centered around f1 plus f dash. So basically when I am going to pass this through a band pass filter centered at f dash minus f1, I will obtain this. So this is what my intermediate frequency is, which is given as f2 in that question if I'm not wrong. Yeah, it's f2. So essentially f dash minus f1 should be f2, or f dash is equal to f1 plus f2. So this is local oscillator frequency. This one here is carrier frequency, and this one f2 here is intermediate frequency. Excuse me for a moment, I will just have a package that I need to collect.
Okay.
I'll be gone for 2 minutes. Sorry about the inconvenience.
No issue.
Hello, Dheeraj sir. Yeah, yeah, sure, sure, sure. Sorry about that, it took more than expected. So as we were discussing, where were we? Okay, the local oscillator frequency thing. So as you can see that local oscillator frequency f dash is nothing but the sum of carrier frequency plus intermediate frequency. But there is one more catch here. You can see here this cos 2 pi f1t times cos 2 pi f dash t. This is just one way of writing, but in place of this I can also could have written it as f1 minus f dash. So in case I would have written is f1 minus f dash, that would be same as intermediate frequency, right? So f1 minus f dash is equal to f2. In that case, the f dash, that is the local oscillator frequency I was trying to find, is f1 minus f2, that is carrier frequency minus intermediate frequency. So actually both are true. So we can have the local oscillator frequency as the sum of carrier frequency and intermediate frequency as the difference between them also. The thing is, when the local oscillator frequency is less than the carrier frequency, it is termed as a heterodyne receiver, whereas when the local oscillator frequency is greater than the carrier frequency, that is f1 plus f2, this is known as super heterodyne receiver, or more commonly just termed as in a short form like superhet. So I guess our question mentioned one of these, either heterodyne or super heterodyne. So okay, it's super heterodyne. So for super heterodyne case, the frequency of the local oscillator is going to be f1 plus f2. We need to be careful. Had it been the heterodyne receiver, it would have been f1 minus f2. So the key principle is, when the local oscillator frequency is greater than the carrier frequency, it's super heterodyne receiver, and when the local oscillator frequency is less than the carrier frequency, is a heterodyne receiver. So with that we move to our next question, which again corresponds to a uniform quantizer with 100 1024 quantization levels and maximum message amplitude of 200. So what is the quantization noise power? This is quite similar to what we have already observed, so we can just directly write the formulas here. So quantization noise power in dB is going to be 10 log base 10 sigma square q. This is the quantization noise power. It's equal to minus 10 log base 10 3 plus 20 log base 10 m max minus 20 b log 2 log base 10 2, where b is the number of bits to represent the quantization level. So we just need to put the values here. It's minus 4.77. In this case it's 20 log base 10 200. So 20 log base 10 100 is 40, and another 2 is left, so log base 20 is 0.3, so that is 6. So this should be 46, and minus 20b, this is log base 10 2, that is 0.3, so again 6b. So b here is going to be log base 2l, where l is 1024. So we'll have log base 2 1024, that is 10. So we'll need 10 bits to represent each sample. Minus 6 into 10. So this is minus 60 here plus 46, so that minus 14, and minus 14 and minus 4.77 is minus 18.77 dB. So the closest answer is the 1. It's not exactly matching. It's 18 point. Let me just calculate once the log base 3. Okay, log base uh, 200 log into 20, 6.023 log. Okay, it seems it 18.77 only, and that can be roughly approximated as 18.75. So this question basically asks, this T1 telephony system is an example of frequency division multiplexing, code division, space division, or time division. So we have already discussed T1 system in details and found it to be time division multiplexing. So T1 system is an example of time division multiplexing, where you basically multiplex 24 voice channels over two separate wires to transmit your composite voice signal. So here fourth one is the answer. Next it's 13, okay, it's 14. So okay, in the delta modulation, the distortion that arises when the step size delta is large in comparison to signal that is relatively fat is termed as which one? Small amplitude distortion, step overload, granular noise, or additive white Gaussian noise. So when you talk about delta modulation, it's a differential modulation technique. First of all, delta modulation is a differential modulation technique. So here we quantize the difference between consecutive samples. So what is the motivation for that? So actually in practice, whatever continuous waveform we see, be it audio or video or image, they are actually kind of smooth waveform. Smooth waveform means there is not like some drastic change in value over a short period of time. So that means what should I say, that it's not something that change value very rapidly in a very short time. So what I am trying to say is that this kind of signal which uh, like changes value in a short period of time, it doesn't see them. In nature we observe mostly this kind of waveform. So let me draw them. So we encounter smooth waveform where the rise and fall of the waveform are kind of slow. So basically when you sample quickly enough, let's say at this point, at this point, at this point, the sample's value doesn't change much. So therefore there is high correlation between the consecutive samples, and that's what is being exploited in the delta modulation. Now we have seen that quantization error is heavily dependent on the dynamic range of the uh, message signal you are planning to quantize, right? For example, if the message signal takes value between, let's say, 100 and sorry, minus 100 and 100. Then to get a reasonably low quantization noise power, you can see we need large number of bits to represent each sample, and that is because we want to reduce the step size, and that is basically same thing as saying as reducing the quantization error. So hypothetically, let's say we need only 10 bits, sorry, not only, we need 10 bits to represent each sample. But now if I plan now this message, if it's a continuous waveform, so there is no rapid rise or fall in the, that is there is no, most importantly there is no discontinuity in the signal, so therefore there is no high frequency component, then the consecutive samples are going to be highly correlated. That means that difference are going to be small. So hypothetically speaking, for the same signal, the difference between the samples have a dynamic range of, let's say, minus 2 to 2. So to actually achieve the same level of quantization noise power, you maybe need to spend 1-2 bits per sample. So basically you are not quantizing or encoding the sample itself, you are basically quantizing the difference between the samples, which have a very lower dynamic range compared to original sample. So that would reduce to drastic reduction in the uh, bits required. So this I'd like to point out, drastic reduction in number of bits required for same quantization noise power. So actually we can send lower to lower number of bits, so my bit rate drops. So that is the main motivation behind the delta modulation. And how do it looks like in practice? It's something like that. For example, you have a message signal like this as shown in the red curve here. So I'll just erase it once. And you do this delta modulation, you do this staircase kind of approximation. So the theory behind is that, let's say this is n minus 1th time instant and this is nth time instant. So at n minus 1th time instant you make a prediction about the quantized message level. So this what I am talking about, quantized message level. This is the prediction at n minus 1th time instant, which now this is the reconstructed version of the quantized and reconstructed version of the message, which is also the prediction for nth time instant. Now you see actually in the nth time instant the message value that corresponds to this purple point here is actually greater than this prediction here. So you can see when the prediction is greater, you actually need to increase, like basically you are trying to encode the difference between the consecutive samples, and if it turns out if the true sample value is greater than the prediction, then you actually move upwards.
Am I audible?
Yes, yes, you are audible.
Fine.
So that is the main goal behind that. Similarly in this case you can see this is the prediction of the message at some one particular time instant, where the message value, the true message sample value, comes out to be lower than that. So essentially you move downwards to track the channel. So in that way you can see this staircase here, this staircase approximation closely follows the message signal. So if you obtain the staircase approximation and you pass it through a low pass filter, we get a smoothened version of the desired message. So actually delta modulation, we even don't employ more than one bit, we actually employ one bit quantization. So it's like it's either plus delta or minus delta, so the things happen something like that. So let me write it down here. This m q n minus 1, this is the prediction for sample at nth time instant. You can also see it as a reconstructed version at n minus 1th instant. Both are true. So this is what is you are going to predict with the sample value, which is actually the true sample value is given as mn. This is your true sample value. So this is what you predicted, this is turns out what your true sample value. So you can see your error is going to be mn minus mq n minus 1. This is what your prediction is, and this is your error in prediction. So this error here you try to quantize. So I'll write down the error expression again. En is the difference between true sample value minus its prediction. We next quantize this error, which is given as EQN, which is the quantized version of En. So since we are using one bit, basically it can take two values. It is compactly written as delta sign of En, where sign of x is equal to 1 when x is greater than 0, and sign of x is minus 1 when x is less than 0. So when basically your true value is greater than the prediction, your quantized error is going to be delta. So it essentially tells you to move delta step, like add plus delta to predict the signal at next time instant. And similarly, when your true sample value is less than the your prediction, then your error is going to be negative, and in that case your quantized error is going to be minus delta. That would basically tell you for the staircase perspective to move uh, downwards to track the signal. So that is how it happens. Now what is the issue when we have this step size delta is large in comparison to a signal that is relatively flat? So when you talk about a relatively flat signal, it looks something of this sort. So this is, you can consider as a relatively flat signal. So what is the characteristics of this? Slope is very small. So that is the characteristics. Now I will draw two cases here. One staircase approximation with large step size and another with small step size, and I will denote them with separate colors. So you can see here, this is what your step size is, delta, and I will have another one with small step size. This one is large delta, and this one is small delta. Now what I want to point out here, when you have a large step size and the signal is relatively flat compared to that, you can see your what is your quantization error is going to be. Your signal is not changing much, but your this step size is very large. Let's pick the uh, case of uniform quantizer. What is the error in that case going to be? It's vary between minus delta over 2 to delta over 2, right? So in that case your error is going to be far greater. By the way, error means I mean quantization error. Quantization error is high. Basically it's the difference between MT and its prediction. So you can see the quantization error varies between, at least for uniform quantizer, minus delta over 2 to delta over 2, and for large delta your error is going to be also high. But in that case, if you use a small step size delta, then your quantization error is going to be low. So as the question says, when the step size delta is large in comparison to signal that is relatively flat, what is the problem that is going to arise? So from this high quantization error, what you are going to see is something called as granular noise. When your signal slope is very small and if you have a high delta value, you are going to see a constantly very high level of quantization error, which is also termed as a granular noise. So to answer the question, it's the granular noise. I just briefly discuss the opposite case also here. So what happens when signal rises very rapidly compared to step size? So this condition mimics this figure here. So your signal increases rapidly means the slope is very high. So this is a high slope, and if you have a lower like small step size, then you will have a staircase approximation of this kind. And when you have a large step size, so this is a small delta and this is large delta. I'm discussing this only because this discussion of only granular noise gives you an impression that, for example, the large step size is always bad and small step size is always good. It's not actually the case. It depends actually on the signal. If the signal starts rising or falling very rapidly, and if you have a small step size, then your staircase approximation won't be able to follow the signal. You can see the blue staircase here is not following the red curve here. So you are going to see a large error. When you actually have a large delta in this case, it's going to help you here, because in that case you can see the black one is properly able to track the message. So it's not about the having a large step size or a small step size. You have to strike a kind of balanced trade-off to, okay, this case by the way is called slope overload distortion. So when the signal is relatively flat, the large step size is going to cause granular noise, and when the signal is rising rapidly and when you have a small step size, it's going to cause slope overload distortion. So essentially you have to strike a trade-off between large and small step size. You have to choose some middle point where both the granular noise and slope overload distortion can be kept in a check. And for example, you actually have an option of adaptive delta modulation, where you can actually adapt the step size based on the signal. For example, in the region when when the signal has a very high slope, your step size accordingly increases. For example, and when the in the regions where signal is relatively fat, signal is relatively flat, your step size you can actually decrease to reduce the granular noise. In that way you can achieve a superior performance. So we next talk about superhead receiver. We have already seen when you say superhead receiver, it means the local oscillator frequency is greater than the carrier frequency. Now the broadcast frequency is said to be FC. FC is basically broadcast frequency, and carrier frequency are the same. And we have intermediate frequency, to which frequency we want to translate the incoming signal to, and the corresponding image frequency is given as follows. Okay. So the concept of image frequency is also interesting. For example, if you have an incoming signal mt cos 2 pi fct, so you multiply this with local oscillator here. For a superhead receiver, it's cos 2 pi fc plus fif t, right? And then you pass it through a band pass filter with a intermediate frequency FIF, and at the end you will have your signal half of mt cos 2 pi FIF t. We have already seen. But what is the concept of this image frequency? Image frequency is considered as basically interference, which has to be taken care of by some RF filter pre-processing even before the frequency mixing starts. And what is the frequency? What is the concept of image frequency? So the uh, let's say the image frequency I denote as f dash here. So let's say here I have a cos of 2 pi f dash t, and then I have cos of 2 pi fc plus fif t. So this can be written as, I have mt is multiplied in the both the cases, but I am just ignoring it because in this discussion it is not exactly required. So I have here cos of f dash plus fc plus fif t. Sorry, it should be a 2 pi. Here we will have a 2 pi fc plus fif plus f dash t plus cos 2 pi f dash minus fc minus fif t. So when we basically pass this through a band pass filter, so this f dash minus fc minus fif, when we pass through a band pass filter for value of f dash is equal to fc, which is our desired signal, we know we obtain fif. So we basically obtain a sinusoid of frequency fif. I am ignoring the negative sign because it's not important here. But there is another carrier frequency which produces the same frequency. You can see here, if I replace f dash with fc plus 2if, sorry, 2fif, and you can replace the f dash value here. So this is basically fc plus 2fif minus fc minus fif. So this also FC cancel, and you have left with FIF. So if you pass this also through bandpass filter, it is also going to create a sinusoid at the center frequency FIF. So it's not only the broadcast frequency FC that would lead to this intermediate frequency component, but also the broadcast frequency value is FC plus 2 FIF. This part will also pass through bandpass filter, and this is the undesired part. This is the undesired part which causes interference to your original signal. Let's say some other message, say let's say m dash is being transmitted over this carrier frequency. So essentially at the output of bandpass filter you will have this plus half of m dash t cos 2 pi FIFT. So that would actually make your job very difficult, especially when your that this signal at this carrier frequency is strong enough compared to this your original message signal. So this image frequency actually need to be suppressed by some RF filter pre-processing even before the frequency mixing starts. So the image frequency we have seen is given as FC plus 2IF. So key part is that here. So this equation, this sinusoid when you pass through bandpass filter produces a sinusoid at this frequency when f dash is equal to fc. But not only this, when f dash is equal to fc plus twice intermediate frequency, this is also going to produce the sinusoid with same frequency, and this is what we have to cautious about. If some message is transmitted over this carrier frequency, it is also going to pass through this filter and cause interference to your original signal, which will degrade your demodulation task. So it's asked if two events A and B are mutually exclusive, then which of the following statement is always true? So basically when it says that A and B are mutually exclusive, that means that intersection of A and B is actually the null set. So these are actually corresponds to events, and if this event A and event B are mutually exclusive, that essentially means there is no common sample between them, like there is no common space between them. So essentially when you take the intersection, it's going to be null set. It's something like this. Let's say this is A and let's say this is B. So if you try to take the intersection of A and B, like which events are basically commons to both set A and B, you will find that nothing is common, and essentially the intersection of A and B is constituted of the null set, and the probability of null set we know is 0. This can be obtained from this probability axioms also, where it says that probability of your entire sample space is 1. So null space is basically the opposite of your sample space. So this is 1 minus p of s composite s bar. So this is 1. So probability of s bar is 0. That is probability of s bar is nothing but the null set only, because if you remove the sample space from itself, you are left with only the null space, only the null set, and whose probability is 0. So if two events A and B are mutually exclusive, you are going to have probability of A intersection B as 0. Okay, we are seeing a lot of uniform quantizer questions. So quantization noise.
Can give work.
Hello.
You can give this question to read by ourselves. We can do it as a homework.
Okay.
They are
Okay.
similar like to others, right?
Yes. 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 So I am leaving this, and the last one is regarding. Okay, this is a superhead receiver which is having a broadcast frequency of carrier broadcast frequency of 2 kilohertz, and your
3
intermediate
kilohertz
frequency.
is the answer.
Actually, I'm not able to hear you. Can you please repeat yourself once?
It is 3 kilohertz is the answer.
So broadcast is
For
two, intermediate is one, corresponding local. It's a superhead receiver. Yes, yes, one. So had it been the only heterodyne receiver, so what should be the answer? Just I'm curious to know. Uh,
this super in that case 1 kilohertz, right?
okay, okay, nice, nice. Yeah, it's FC minus FIF. So essentially, the local oscillator frequency is less than the broadcast frequency. So yeah, had it been only heterodyne receiver, it would have been 1 kilohertz. Nice.
And super it is a 3 kilohertz. Am I right?
Yes, yes, yes. It's the
Yeah.
broadcast frequency plus the intermediate one. Okay, so with this, if you have any questions, or I can, if you want me to clarify on something I've discussed till now,
Can you
yeah.
share your email ID, so if we have any query we can write you the
Okay, okay,
on your
sure.
email.
I'm writing it on the this chat box. Can you just
Uh,
copy it, right?
yeah.
Just a minute.
So you are a student right now with
Ye-
IIT Kanpur.
yes, yes, yes. Yeah, I have sent it. Can you please check it whether you have received it?
Get
Okay,
it.
okay,
Got
okay,
it. Got it.
okay.
Thank you so much. Thank you.
Yeah, sure.
If it is possible, if you have time permits, let's solve those questions, the homework one.
Okay,
So I think rest of the people can get an idea.
okay, okay, sure. I think in I just need to write the formulas and
Yes.
this one, right? So the quantization noise power again, it's log base 10 sigma q square is minus 10 log base 10 3 plus 20 log base 10 maximum message amplitude, and
So we can write minus 6b directly and 4.77 directly, right?
yes, 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 we can write them directly only. So it's, as you said, it's minus 4.77, then we have 20, it's 500, so it's going to be, and to calculate once, 500 log
For
20.
this kind of calculation, we require a calculator in the examination, right?
Yeah, like
So,
last time I checked the guidelines, most likely scientific calculator is allowed. I'm not very sure about that, but if I'm not wrong,
no,
it's allowed. But like
okay,
I'm not 100% sure.
okay.
So it's 53.97 here, 53.97, and then we have 256 quantization level. That means 8 bits. So it's 6 times 8, 48. So it's going to be 48 plus minus 52.77, so it's 1.21 dB. It's not exactly 1.21, it's 1.20, but yeah, fine only. So third one is the correct answer. So if you have any other doubts or queries regarding today's session, you can ask me, or otherwise I'll just conclude the session. And you can, by the way, always ask me questions over the emails and all. I will try my best to solve any doubts you have.
Thank you so much. Thank you so much for your time.
Oh, sure, it's my job only, so no need to thank.
So no question from my side.
Okay, okay, okay. So then I'm concluding this session. We'll meet in the next week then. Actually, next week you all will get a notification. The this will not happen on Saturday. It will happen on Sunday instead. The timing will remain same, 3 to 5 only. But instead of
Sunday.
Saturday, it will be
Okay,
on
fine.
Sunday. Okay.
So
Okay.
before the deadline of the assignment, right, we'll solve the question.
Yes. Yes. Yes.
Okay,
Yeah.
okay, fine.
Yeah. Thank you.
Fine. Thank you.
Bye. Bye.
Yes, bye. Have a nice day.
You are saying something?
I'm just say have a nice day.
Okay. 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 Yeah. Sure. Sure. Same. Same to you too.